Hello, everybody. Good morning or good afternoon. We're going to just wait 2 minutes to allow more people to join us. So please be patient and we'll be with you in 2 minutes. Okay, well, we'll get started now. Welcome, everybody. For those who don't know me, my name is Paul Scotchless. I am the Artificial Lift Product Champion at PCM. I've been at PCM for about 2.5 years, but I have 25 years working with PCPs in the industry. Welcome to the latest in our series of webinars. I don't really think this is number 7 or number 8. I don't remember now how many we've done, but if you've seen some of the previous ones, welcome back. And if this is the first one, then thank you for coming. Today we're going to be talking about energy efficiency, so I'll just go right into the presentation here, and we'll get started. So energy efficiency improvements for PCP systems is our topic today. So just a quick illustration of why this is so important. Why are we concerned about it? Obviously, there's other reasons. Companies have their net zero targets and things like that they're trying to reach. But if we just look in terms of money, if you have a 100 horsepower system running at full load with 95% efficiency, and you're paying 15 cents a kilowatt hour, then you're paying over $100,000 a year for electricity. Obviously, it's a lot of money. Each percentage point is $1,000 a year, more than $1,000 a year, whether that's a point of efficiency or power reductions. So you can look at it either way. So we look at reducing the power the system requires by improving the design, or we increase the efficiency by worrying about how our belts and shivs are maintained and things like that. Either way, you're looking at over $1,000 a year for every point of efficiency you can gain for a system that size. Now, if you've got multiple wells, of course, and if you've got 100 wells, then 1 point of efficiency is $100,000 a year through your field. So it's clearly, even though it looks small, 1%, it can be substantial if you've got a lot of wells running a lot of power. Obviously, if you got smaller power wells, then you're going to scale down appropriately. But just an example of how much money is at stake here. So let me just have a quick look at what is energy efficiency. A couple of different ways to look at it. How much energy did you have to put in to get a certain amount of energy out? Or how much energy did you put in compared to the theoretical amount of energy it should have taken? So if you remember back to your thermodynamics classes in school, they talked about first law efficiencies and second law efficiencies. We're not really going to look at all of this. what really we're concerned about is what's your power consumption. When you look at a whole artificial lift system, efficiency is a bit complicated. For a pump, it's pretty simple, especially if the fluid's incompressible. Power out is pressure times flow rate. Power in is torque times speed. Efficiency, you just calculate one divided by the other. But when you look at a whole system, now you're looking at, the reservoir has its own energy. You put gas in solution, and that has some energy in it. Elevation changes are involved, because obviously you're pumping from depth to surface. What pressure are we starting from? Do we consider reservoir pressure or the flowing bottom hole pressure? There is not a well-defined definition of efficiency that you can really use for artificial lift systems. For a pump in itself, yes, there's a definition of efficiency, but for a whole system, it's much less clear. So I'm not really going to get into efficiencies in this, with one exception you'll see on the next slide. But really, we want to look at how much money does it cost to get your oil to surface or your gas to surface. There are some people have used metrics like kilowatt hours per barrel per 100 meters of lift or something like that. And that's, it's a good metric for comparing similar applications, but when it's only looking at depth and ignoring reservoir pressure, it's still not a complete measure of efficiency. So again, I'm not going to talk about efficiencies for most of this presentation. We're just going to look at energy consumption and how to reduce that. So this paper, or this picture came out of a paper from 1993, I think it was. And it just compares some artificial lift systems, and it's using efficiency. It doesn't define how it calculates efficiency here, so they have their definition of efficiency, but they didn't define it. But I think the overall picture is accurate here. We see the PCPs can have the highest efficiency of any of the artificial lift systems that are listed there, which is the major ones, of course. Now, when I show this picture to people, I always want to clarify that the range that's shown there is valid for well-designed systems. Certainly, you could have a PCP system or one of these other systems that has an efficiency that's much lower than what it shows on there if it's a poorly designed system. But what we're seeing here is that the PCPs have the possibility of having a higher efficiency than other systems. Or if we want to, again, look at power consumption, to get that fluid to surface, it takes less power with the PCP. Here's another example that I just got recently. It's not published data, so I can't share the source. But it was just one company had looked at their power costs for their different forms of artificial lift that they were using in a field, and they had presented it in I think it was just kilowatt hours per barrel or something like that. I don't even think it had a depth metric in it. So presumably their field is all one depth, and they didn't feel the need to include that in their metric. So I've scaled it here with the PCP being 1, a standard rod-driven PCP being 1. Sucker rod pumps are about 30% more power for this field. The ESPs are quite a bit more. So this is maybe a field that's not appropriate for ESPs, because when we looked at that previous slide, there wasn't that much difference between the PCP and the ESP. But for some reason, this field, they're spending a lot of power when they run an ESP. On the other direction, when they tried putting a PMM drive head, and we'll talk more about those later, on the well, so it's still a surface-driven PCP, but with a permanent magnet motor drive head, they saved about 25% of their power consumption. And when they went to an ESPCP, so you're running a PCP downhole with an ESP driven system, ESP motor, PMM motor downhole, they saved about 60%. So there are certainly some areas to save power, even when you are using still using a PCP as the pump. And again, this is one field. Other fields with different conditions, if you have different viscosities, different gas amounts, things like that, you might get very different results. But I think the general trend here is accurate. The PCP can be better than the sucker rod pumps or the ESPs for power consumption. And when you start looking at permanent magnet motors or ESPCP driven systems, you have some opportunities for improvement. So in this presentation, we're not going to define the efficiency. We're just going to look at power consumption. And we're also, beyond what was on those previous two slides, we're not going to compare the PCPs to other artificial lift systems. I presume when you've come to watch a presentation from PCM, you're interested in the PCPs, and we're going to talk about how to reduce the energy consumption in our PCP systems. So the options that are available to us depend on certain things. Is the well horizontal or deviated vertical? Horizontal or deviated wells, we're going to worry more about the rod string than we would a vertical well. Is there gas production? Do we have to worry about gas separation? What size of pump do we have to run to deal with that? What's the viscosity of the fluids being produced? And we'll deal with all these questions. And many times there's limits on what we can do in a well. There may be technology available, but we can't use it in our well for some particular reason, such as casing size, or simply not available in our area, or the type of power source that we have. Even something as simple as having crews that know how to install a certain type of equipment. When you want to bring new equipment into an area, you either have to bring in people to train them, train the crews how to install that, or you bring in a crew from somewhere else, or maybe you just decide that's not worth the effort and we're going to look at only what we can do with what we have locally. Costs may not justify the benefits. If you're going to spend a huge amount of money on a very energy efficient system, that might not be worth the effort for you. Depends on your OPEX versus CAPEX questions, whether there's constraints in your area for cost of energy or cost of carbon. If you have limited power availability, then you may be willing to spend more money as well. And again, safety or practical reasons for some options. There may be some types of belt and shiv systems, for example, that for safety reasons you don't want to use a certain type of system. So again, we're going to look at reducing energy consumption, but you should be looking at a full life cycle carbon analysis or life cycle cost analysis, whichever way you want to look at it. Cost analysis will probably include carbon in it, of course. So by spending more money up front, you save money later on. Is that a good thing? Is it good enough to justify that upfront cost? Those are questions which are beyond the scope of this presentation, but something that you certainly should be looking at when you're designing your systems. Things that we're going to look at: selecting and maintaining the surface equipment, rod string design, tubing size, optimizing the pump size, alternative drive systems. And we're going to use a couple of different wells in this presentation to compare things, but we'll start with this one, producing 50 cubic meters a day of basically water from 1,000 meters with a low submergence. Cost of electricity 15 cents a kilowatt hour. And then just to get a fair comparison, I used an industry PCP design software to calculate the power requirements for each of these different cases up to the polish rod. I didn't use that software for the drive equipment because it uses certain assumptions that I wanted to be able to use different assumptions to show you in this presentation. So I calculated the polish rod power using the software, and then beyond that is just using the efficiencies that we're going to discuss. Oh, if that well was vertical with water and I've installed a PCM 24E1300 with its friction torque and efficiency as per the data sheet, then we have a power at the polish rod of about 9.3 kilowatts or 12.5 horsepower, and the system's running at 247 RPM. So that's our base case. Now you always some friction in the stuffing box, drive head bearings, other things like that. So let's assume perhaps a difference of 20 Newton meters between a well-designed system and one that maybe is over tightened or hasn't been greased recently or something like that. So that extra 20 Newton meters of torque at 247 RPM, it's 517 watts, which will cost you about $680 a year. So again, if you've got a lot of wells, you've got 100 wells that are each perhaps over tightened or not lubricated properly, adds up to a lot of money. Looking at your belt system, if it's maintained properly, so we look at we looked at the stuffing box. Now we'll look at the belts. If belts are properly maintained, so they have the right tension in them and they're properly aligned and they're not worn, they can be up to 98% efficient. But if they're not tightened properly, if the shivs are worn, or if there's any kind of misalignment between the shivs, then your efficiency may go down to 90% or even lower if you start having all of these problems together. So the difference between 98% efficiency and 90% efficiency in this well adds up to over $1,000 a year, $1,113 a year basically, with the difference between 90% and 98% on the belts. So certainly you want to be looking at your belts, make sure the shivs are aligned, the tension is correct. So I know some product manuals for PCP drive heads will say the tension is correct if it's just tight enough that it's not slipping. And that's probably a good way of looking at it. You don't want it to be too tight because that puts more stress on the bearings and everything, but you don't want it to be loose enough that it's slipping. The belt and shiv manufacturers themselves will actually give you recommendations for how to measure tension on the belts by basically you press in on the belt and how far does it deflect from a straight line with a certain amount of force on it, and so you can look at the documentation from the shiv and belt vendors for that. You might not find it in the drive head manual. But also inspecting them for wear. So there's a picture on this slide that shows a little tool that fits into the groove on the shiv to measure how much wear there is, or to visually show if this shiv is worn or not. So again, you need to have those correct tools for your shivs and follow the manufacturer's procedures for determining if a shiv is worn and replacing them when they are significantly worn, of course. So we had two examples here. We had the friction and the belt efficiency. When you have multiple sources of inefficiency like this, you don't just add the losses together. They actually have to multiply, because you got the extra friction there, but now that efficiency on the belts is also being applied to that friction. So you have to consider this multiplicative effect. So if we do both things, so you see on the slide there, if we have the low friction and the high efficiency, our input power is just over 10,000 watts. But if we have the high friction and low efficiency, it's 11.5 kilowatts. The difference of about 1.5 kilowatts or $1,900 a year, which is a little bit higher than what we would have got if we just added those two effects separately. So when you have these multiple sources of inefficiency, you do have to multiply them, and they all apply to each other instead of just adding them up independently. So looking at selecting your surface equipment, there are a lot of people who do use hydraulic systems with their PCPs. There's reasons for that in certain areas where it can be very useful, but they're not very efficient. So if you're looking at if energy cost is your primary concern, you're probably going to do whatever you can to avoid using a hydraulic system, simply because you've got a pump, a motor, some hoses, some valves, filters. You lose some energy in all of that, and it all, again, that multiplying effect, you end up having a fairly low efficiency in that system. Gears are pretty good as well. If you're having a gear-driven system, the efficiency there is about as good as well-maintained belts, so they can be quite efficient, and you don't have to worry about things like alignment and shiv wear. But if you have a system that uses gears and belts, again, that multiplicative effect applies, so you have this efficiency on top of an efficiency. So again, with the example we have here, 96% efficient belts, 96% efficient gears, with our polish rod power of 9,300 watts, that's a difference of about $500 a year if we're using both systems as opposed to just one. Now, there are times when that is a good thing, that you would need to use gears and belts, particularly if you have a high reduction ratio. If you want to be running your PC pump downhole at 75 or 100 RPM, you need to have a pretty high reduction ratio. Either that or you've got a VFD that's running at a very low frequency, and you're going to lose efficiency there too. So if you are running at low downhole speeds, then those systems are probably the best thing you're gonna have. But if you're not running at low speeds, if you're running at moderate or higher speeds downhole, then probably not having both gears and belts would be the best. Types of belts. Standard V belts are very common. The notched ones are better. And when I say notched, I'm not talking about synchronous ones yet. We'll talk about that in just a second. So in the picture here, bottom one is the synchronous ones that have the teeth on the sheave. The top one just has these notches in the belt, but the sheave is still the same sheave that you use with the standard V belts. The only difference is these notches in the belt, they make the belt more flexible. By being more flexible, it loses less energy every time it goes on and off of the sheave. So the notched V belts, they're used with your same standard sheaves, but you're gonna get a little bit better efficiency out of them. The synchronous belts in the bottom picture here, those will give you even higher efficiency. I don't think they're commonly used on PCP systems though. I think some people are worried about if the pump gets stuck and the torque is too high, then something could break. If you have a proper shutdown on your system, that really shouldn't be a big concern, but I understand that some people are concerned about that. So we don't see those very often in the PCP systems, but if you're trying to get every percentage point of efficiency you can, then that's something you can look at. Permanent magnet motors have about 5 to 10% higher efficiency than induction motors, and it is possible to buy a permanent magnet motor that's the same size and shape as your induction motors, so you could just simply swap them out. Take the induction motor off your drive head, put a permanent magnet motor on, and gain those 5 or 10 percentage points of efficiency. But really, if you're going to go to a PMM, the PMM drive head, where it's a large PMM there's no belts, there's no gears, and it's just a big motor with a hollow shaft with the polish rod comes through. That's the way to get the best efficiency from a surface drive PCP system. So if we look at an example here, a 95% efficient PMM, compare that to a 90% efficient induction motor. It's only 5% improvement on the motor there, but also you're losing another 4% with the belts. The difference there in our example here, our 12 horsepower example, is $1,200 a year. Obviously, if you have a bigger power system, that's gonna that amount will increase very quickly. Just as comparison, in this graph here, we actually have, this is real test data that we had at PCM. We had a PMM drive head, I think it's about a 50 horsepower system that we brought in and put on our test bench here at Chantilly in France. And we compared it against one of our PCM drive heads, and we measured the current and power consumption at a range of different speeds and torques. And you can see for each of the two drive heads, the speed made almost no difference to the efficiency that was being measured. But obviously the big difference between the PMM drive head and the standard one. So we're looking at whatever losses there are in the motor itself, of course. On the standard drive head, there's belts and sheaves, the little lubrication pump that's built into that drive head as well. All those things it will take a little bit of energy. And we can see there's a fairly substantial difference here between the two. At higher torques, the standard drive head is much more efficient. So this is something to be aware of. Sizing your equipment properly, particularly electric motors, should be sized so that they shouldn't be oversized too much for the application. If you need a 50 horsepower system, buy a motor that's close to 50 horsepower. Don't go in with a 100 horsepower system, because if you're running at half power, it's not going to be as efficient. And same thing with installing a drive head, putting a 100 horsepower drive head on a well that only needs 30 horsepower. You're probably going to have some losses, some extra efficiency losses there. So in this example, if we run at about 1200 Newton meters and 200 RPM, the difference in cost here between these two applications. So this is not the same example as we were looking at before. This is a higher horsepower example. That's about 25 kilowatts or 34 horsepower here. And the difference between these two motors at 15 cents a kilowatt hour is about $10,500 a year. So now you look at what's the price difference between the PMM drive head and the standard drive head. And you look to see, well, yes, the PMM drive head costs a bit more, but if I'm saving $10,000 a year, maybe that's something I can justify. Looking at rod string design in a deviated well or a well with viscous oil in it. So in a deviated well, there's friction between the rods and the tubing. Friction is just wasted energy, basically. Anytime the well's not perfectly vertical, there's going to be contact. I always like to say there's no such thing as a vertical well. But really, once you get into the significant deviations or horizontal wells, that's where this can really be an issue. The more that friction torque will increase, the more contact load there is between the rods and tubing. Also, the diameter of the rods or where the contact is, and the friction factor between them, and speed, of course, will affect that as well. In terms of the amount of power, so it doesn't, speed won't change the torque very much, but it will change the power. You can decrease this torque. Obviously, once the well is drilled, you can't change the deviation of the well, of course, but so you're dealing with that. But what you can change is the diameter of your rod string, or more importantly, the diameter where the contact is between the rods and the stationary tubing wall. So using spin-through rod centralizers, that contact diameter between the rotating part and the stationary part is much smaller than it would be with a coupling. So the spin-through centralizers can actually significantly reduce the torque associated with friction, but also a continuous rod is actually even a little bit better. So in deviated wells, I would certainly recommend the continuous rod. So with that, going back to our comparison well, but now making it deviated, just shows some issues there, and says, comparing a 1-inch rod with full-size couplings to a 1-inch continuous rod, it's over $3,000 a year that we're saving in this particular well, going through about a 5-degree dogleg through about 400 meters of the well. So there's that section of the well with that torque. So it's a fairly substantial difference there. Whether $3,000 a year justifies going to continuous rod, that's a question you'll have to ask. But certainly looking at, if you look at the torque numbers here, going to the spin-through centralizers is getting most of the way from where you were at 137 Newton meters of torque down to 73. It's a pretty big step. You can get to 61 with the continuous rod. So you can save most of that $3,000 by just using the spin-through centralizers, if continuous rod's not an option for you. If you have high viscosity fluid in your well, then it takes some torque simply to rotate that rod in that high viscosity fluid. And it's proportional to the viscosity and the speed. There's some effect of rod and tubing sizes, but it's less. It's not a huge effect of rod and tubing size, except where there's small clearance between so if you have large couplings and small tubing, there can be a substantial viscous torque on those couplings. So in our well, if we had 1,000 centipoise of fluid, with our 1-inch rods, we've got 66 Newton meters of torque to simply rotate the rods. Now, in the example here, I can't get rid of that torque, of course. So what I'm going to try and do in this case is I'm going to put a bigger pump in. So I'm changing from my 24E 1300 to a 63E 1200 to be able to run at a lower speed. And running at the lower speed, it drops that viscous torque from 66 Newton meters down to 25 Newton meters. Plus, we're multiplying by the speed because it's power is torque times speed, and this gives us a savings of about $2,200 a year, simply by just going to that larger pump. And that's not counting the friction torque on the pump. I think the 63 1200 actually has a lower friction torque as well, so we actually save some money there in terms of power as well. So it's just a question of the cost of the pump itself. In viscous wells, tubing size, obviously, if you're running a high viscosity fluid, the first thing I'm going to recommend is going to a larger tubing. Reduce your pressure load, makes lower load on the pump. You might be able to use a smaller pressure rating on your pump too. Reduces your power consumption. It's just generally a good thing to use the larger one. So the base case, we use 3.5-inch tubing. If we increase that to 4.5-inch tubing, we save $2,200 a year in this example. On the other hand, if you went down to 2 7/8 tubing and had to switch to continuous rod because you couldn't use those full-size couplings anymore, that would add over $3,600 a year. So big difference between the tubing. If we compare the 2 7/8 to the 4.5 inch, you're looking at over almost $6,000 a year, $5,800 a year. So the tubing size certainly makes a big difference there. If you have the opportunity to use larger sizes when you have high viscosity fluids, that's generally a good thing. Gas going through the pump. There's a bunch of different effects of gas, and some of them are good, some of them are bad. A little bit of gas, especially if you have a viscous fluid, can decrease the viscosity, decrease the density a little bit, and can help reduce the power requirements. But if you have too much gas going through it, you have to run the pump faster or run a bigger pump. Either way, you're putting more power in. So probably a little bit of gas is good, but too much will reduce the overall efficiency, increase the power consumption. So running a gas separator, if you had a lot of gas, running a gas separator could probably be a good thing to do in that case, to try to reduce your power consumption. You do have to do an analysis for these things to decide what the best results are. If you do have gas going through your pump, at PCM, we would always recommend running the PCM slugger to maximize the pump life when you've got gas going through a progressing cavity pump. PCP systems, electrical submersible progressing cavity pump. Generally, these all use a PMM, which have higher efficiency. The PMMs are perhaps not used because of the higher efficiency, but they're used because they can run a high torque and low speed, which is good for a PCP application. The higher efficiency is just a side benefit, I guess. These are really good in applications where you need to avoid any problems with the rod string, so deviated wells in particular. But again, we showed you the improvement in efficiency from by going to continuous rod by reducing that friction. If you get using ESPCP, you get rid of it altogether. So there can be substantial savings there in terms of efficiency in a deviated well. No friction at the stuffing box. Of course, no belts or shivs or anything like that at surface either. So there's some areas of savings there. And if you have viscous fluid, the pump you no longer have a rod string in your tubing. So by not having a rod string, higher flow area, less pressure losses. So there's a lot of areas for benefits here. And that example I showed from one company's results showed they had a 60% reduction in power consumption with an ESPCP. And we have another one. I didn't pull up the paper for this presentation, but we did run an ESPCP in the Middle East where they showed the same thing. I forget what the percentage decrease in power was, but it was also substantial. Now, what's not considered on this slide here are electrical losses in the cable and transformer, but in a well-designed system, those should be fairly small, and the net effect is definitely a significant improvement in power consumption or reduction in power consumption. Pump optimization. There's a lot of different things to look at when we talk about pump optimization, and some things may be more important than the energy efficiency. For example, anything that's going to affect run life of the pump. If you're dealing with high viscosity fluid or high solids, then the geometry of the pump is very important. So it limits what choices you're going to make in terms of your pump selection, because without good pump performance, you're not going to get good efficiency either. So in the example we're going to do in a minute here, we're not going to look at those geometry considerations or diameter considerations, what's the casing size and all that. We're just going to look at some available pumps and see which ones give the lowest overall power. But obviously in the real world, there are other factors you have to look at as well. Friction torque is obviously the biggest concern here. So there's really, I guess there's two sources of inefficiency in a PC pump. One is the friction torque, and the other is the volumetric efficiency, leakage inside the pump. You take those two things together to get the total efficiency. So we want to get good volumetric efficiency while minimizing friction torque. So what's the pump size that we use, the pump fit that we need to get the rotor size to get that result? If we make a pump that's too tight, well, high friction torque, we might get high volumetric efficiency as well, but we'll have high friction torque. If it's too loose, we'll have lower volumetric efficiency, but lower friction torque. So there's going to be a balance in there somewhere where we get the best. And at PCM, we have our own recommendations for that. But in general, you don't size a rotor that's tighter than it needs to be, and don't pick a pump with a pressure rating that's too high. If I've got a well that only needs 600 meters of lift, but I put in a pump that's 1,200 meters of lift, I'm probably gonna have twice the friction torque that I need for that application. If I put in the more appropriately sized pump, I could reduce the friction torque, all else being equal. So again, looking at what's appropriate for your well. Other factors in there, different pumps. If I put a bigger pump, it's going to run at a lower speed. Lower speed means less power loss in terms of the friction between the rods and tubing or in the stuffing box in the viscous drag, but more torque on the pump itself, of course. That big pump might need bigger rods, which then leads to lower pressure losses or higher pressure losses. So these are all things you need to consider together. If I'm running at a lower speed, I might have lower volumetric efficiency if it's a low viscosity fluid. Another thing to look at. Another thing to think about, which I'm not going to get into any detail here, but just something that you can look at if you have a high viscosity fluid, is diluent. There are some places in the world where they do put diluent in the wells, where they have especially high flow rates of high viscosity fluid. Adding some diluent can really reduce the pressure losses and improve the ability for that to pump that fluid to surface. You're obviously putting some energy in there. You're pumping diluent down the well. There's very little energy involved to pump it down the well because gravity's helping, but you do have to pump it back out. So the pump downhole has to be sized to pump a larger volume of fluid, and you're putting in the energy to pump a larger volume. But if you've greatly reduced the pressure losses, the net effect can be positive there. So you need to design those systems appropriately. But that's an option that does exist. So in this slide, we're looking at the efficiency. So the dashed lines at the top of the graph here are the volumetric efficiency curves that we're used to seeing for PCPs. The total efficiency down below, we don't generally show those in the PCP world. PCM, for example, our data sheets don't have these graphs on them. They just have the volumetric efficiency. So volumetric efficiency, again, usually highest at zero pressure, decreases as the pressure increases. And with speed, higher speeds, higher volumetric efficiencies, generally. If you calculate the total efficiency with zero pressure is always going to be zero because you're putting energy in, there's friction torque. You're putting that, but you're not getting any fluid power out. There's no differential pressure. The fluid hasn't actually gained any energy here. So the efficiency is always going to be zero at zero pressure. Very quickly goes up once you actually start generating some pressure. And then it starts tapering off again once the volumetric efficiency starts decreasing and you start losing that energy due to slippage. Then we start losing that power again. So on these total efficiency curves, you're going to get a maximum point somewhere in the middle. And as you can see, just like when we increase the speed, we increase the volumetric efficiency. We also increase the total efficiency when we increase the speed. But when we increase the speed, we also move that best efficiency point, is what they call it in the ESP world. We also move that to the right. We get it at higher pressures at higher speeds. So if you're sizing a pump, you can consider, again, the effect of, is it better to have a bigger pump so I can be running at a lower part of its rated pressure? But at the same time, if I do that, I'm probably going to have higher friction torque. So what's the net effect going to be? It's where doing an analysis is the best way to look at that. So we'll do an example for in just a minute here. The equation at the bottom is just how total efficiency is calculated. Energy out is flow rate times differential pressure. Energy in is torque times speed. Of course, you have to have the units correct or putting the correct conversion factors to get the actual efficiency out, but that's the basic equation. And here's an example. It's a different example than we used before. This is a bigger well, 200 cubic meters a day of water, basically from 1,000 meters. And just to be consistent, we'll use 3.5-inch tubing, 1-inch drive rods, and spin through centralizers through the deviated section. The volumetric efficiency for each of the pumps that I'm listed is going to be adjusted for speed as per the PCM data sheets. And the friction torques, of course, are also off the PCM data sheets as well for these, the 6 pumps that I've got listed here. So all else being equal, I just put these pumps in, adjust the efficiency, the volumetric efficiency based on the speed, and I get these results here. So somewhere between just under $44,000 a year to upwards to about $5,500 a year, or $1,000 a year of energy costs for these systems. So there's a fairly big difference. There's over $10,000 difference between the lowest and highest there. So now you're gonna look at, what's the cheapest one here? It's the 63E 1200. Is there any other reason why I can't run that pump in this well? If that's not appropriate for some reason, then I can pick one of the other ones. I might want to avoid, for example, this 48E. Given the situation, maybe there is a time when I would want to run that in this particular well, and that would be if the casing's small. This is a 2 7/8-inch pump, where all these other pumps are larger diameter. So if I had small casing, I might not have a choice in this application. If I want to get that rate out of the well, I might have to use the smaller diameter pump, even though the efficiency costs are a bit higher. So again, when you look at the different pumps and pump optimization, I think really the only way to do it is to use the design software, whether that's a commercially available software, or at PCM we have the PCM design software as well, which is an online software. And you can consider, you should be considering the friction torque for the pumps you're using, as well as what's the effect of the efficiency based on speed and pressure, and even viscosity, to get to see what the actual effects are going to be. So just a quick summary: high viscosity fluid, use large tubing. In deviated wells, design the rod string, particularly with continuous rod or spin through centralizers. Consider using PCP. For your surface drive system, avoid hydraulics unless you really need them. Avoid using belts and gears unless you need to have the high reduction ratios. Use the highest efficiency motor possible. Consider a PMM drive at surface as well. Effective gas separation. Consider effects of friction torque versus displacement versus volumetric efficiency on the available pumps. So really, looking at those different designs and putting through some software is probably the best way to do that. Maintenance, making sure your system is properly maintained, especially belts and shivs and stuffing boxes. Making sure they're properly maintained. Belt tightness is correct. Inspect the shifts for wear and alignment, and monitoring consumption over time. Generally, things change in the well as well. So if you're just monitoring power consumption over time, it might be difficult to see if it's a surface problem or if it's just something changing downhole. But the more information you have, the more you can learn from that. Well, I'm going to finish off at that point, and if you have any questions, please type them into the Q&A panel in Teams, and we will go through and answer those. There is a bit of a time delay in this Teams format here, so I see there's 4 questions here right now, or 3. No, just 2. Sorry. I'm going to go through here. I'm going to try and answer these questions. But if you have another question, please type it in now, because by the time I finish these, if you wait until to type in your question when I'm done, the time delay may be such that I actually log off before you have a chance to do that, because you're hearing what I said probably about 2 minutes ago. So please go ahead and just type your questions in now. The first one says, how do you determine the efficiency on the surface equipment? And again, one of the slides I showed earlier says it's very difficult to define a total system efficiency. If you just want to look at the efficiency of the surface equipment itself, how do you determine it? You have to be measuring the power in and the power out. So if you have and essentially nobody does that. So it's how do you determine it? It's really quite difficult to actually determine it. What you do have measured is your electrical power consumption. VFDs will tell you a torque number, but they're making a bunch of assumptions on things like the power, the drive head efficiency and things like that. So you can't use that to determine efficiency. You can't put that torque into the calculations to determine that. I know there's, well, theoretically, there exists devices you could put on your polish rod to measure polish rod torque. I saw one recently that's apparently on the market. I haven't seen any results from it, but if you could actually measure the torque there and then compare that to like electrical power you're putting in, then you'd be able to determine that efficiency. But I mean, unfortunately, no, you can't really determine that efficiency very accurately at all. All we can do is make sure we're optimizing it by doing things like using the notched belts. By making sure we have good alignment, by making sure the belt tightness is correct, the stuffing box is adjusted properly, and things like that to get the best results. But actually measuring it is almost impossible. And the next question there says, do PMM drive heads lose efficiency due to magnetic strength loss at high temperature? I think the short answer to that is no, because the drive head, the PMM drive heads at surface, they're not exposed to the high temperature downhole. They're just sitting in atmosphere. So even when if they're running at high power, they're going to heat up a little bit. They're still going to be well below the temperature that the magnets start losing their strength. And even the PMMs that go downhole, the PCP systems, most of those are designed to operate at temperatures that are well above where we're ever going to run a PCP. So even those, there may be some loss in those applications because they are exposed to well fluid and they're going to get a bit hotter. But even those, they still operate at very high efficiencies. So I'm not aware of that being an issue for any of the PMM systems that are out there. Theoretically, it is a good point that magnets do decrease their strength at temperatures, but for the modern magnets they're using the PMMs, that temperature is just so high that it's just not an issue, particularly for the surface drive ones that are just in atmosphere. They're not even exposed to well fluid, and they're very large in terms of surface area to dissipate that heat. So not generally an issue for any of the PMM systems that are out there. Theoretically, it is a good point that magnets do decrease their strength at temperatures, but for the modern magnets they're using the PMMs, that temperature is just so high that it's just not an issue, particularly for the surface drive ones that are just in atmosphere. They're not even exposed to well fluid, and they're very large in terms of surface area to dissipate that heat. So not generally an issue. How do you calculate the surface equipment efficiency? I had that question in when I did the session yesterday as well. Unfortunately, you can't. There's no way to look at your surface equipment and see what the efficiency is. What you can measure is your input power. The VFD or your current measurements obviously will give you how much power you're putting in. Sorry, let me just instead of seeing my email address, you can actually see my face here if I press the right button. So yeah, so you can't measure it directly. You can measure your power consumption, but there's no way to measure how much is coming out. If you could directly measure your polish rod torque with an actual load cell on there, then you'd be able to torque times speed is power. It's going to the polish rod, and then you can measure the electrical power in. You cannot use the VFD for this though. So when the VFD estimates torque, it's making some estimates on things like drive efficiency. So you can't use that to calculate drive efficiency because it's built that into the estimate. So you would have to have some way to directly measure the polish rod torque. I have seen one website that lists a tool for doing that. I know my previous employer built a tool 25 years ago, but it's not commercially available. But I did see one is available. You would actually have to have that to be able to calculate surface equipment efficiency. Other than that, you're just looking at, the belt manufacturers or the gear manufacturers or the hydraulic pump manufacturers or whatever, and looking at what they're saying their efficiencies are. So next question is, can we speak about a best efficiency point with a PCP as we do for ESPs? As I showed you on that graph a couple minutes ago, yes, it exists. There is a best efficiency point. We don't usually worry about it for PCPs though. Especially when you're running at those lower speeds. You saw on the one graph at 100 RPM, the best efficiency point was somewhere, I think, less than half the rated pressure of that pump. We wouldn't normally operate there. We're going to operate at something more like 60, 70, 80% of the pump's rated pressure is where we're normally going to operate a PCP. So we can speak about the best efficiency point, but we're probably not going to worry about operating so close to it the way that they do with an ESP. If we had to select a different pump because we were trying to operate right at best efficiency point, now we've got to put a higher pressure rating pump in. It's going to have a higher friction torque, even though the best efficiency point might be there. We might end up be putting more power in because we're going to have that pump with a higher friction torque. So in ESP world, they worry about that best efficiency point because they have the up thrust and down thrust issues and things like that. There's other reasons than just efficiency for operating near the best efficiency point. We're in the PCP world. Generally, we're going to be operating at something a little bit higher pressure. So we're going to be probably to the right of that point. And it just doesn't matter the same way as it does with an ESP. Next question says, the pump efficiency chart shows the total maximum efficiency at 4,000 kP on a 12,000 pump. So I think that's what I was just talking about. So if we overstage pumps to put in the high efficiency range, right. So I think this is what I was just referring to. So yes, at 100 RPM, we saw that the best efficiency point was substantially, lower than the pressure rating of the pump. So someone might look at that and say, well, I should put in a much bigger pump then to be able to operate at a higher efficiency. And if I do that, that higher rated pump will probably have a higher friction torque. If I take two elements of a pump and put them together, two stages, put them together, logically it should have twice the friction torque of just the single one. So if I've doubled the pressure rating, now I've doubled the friction torque. So I'm not looking operating at the same pump. That extra friction torque is going to have some effect on the amount of power consumption. So maybe your total efficiency might be better running at that with that higher pressure rating, but your actual power going in is going to be a little bit higher as well because of that extra friction torque. So you'd have to run the analysis, and that was why I did that slide with the different pumps on it. Now those pumps all had the same pressure rating. So it would be an interesting analysis to do. Perhaps I can do that and share it with you if you send me an email. I'd be happy to do that analysis and look to see with the different pumps. If I put a 2,400 meter pump in that well, for example, what would the effect be? So it's again, doing that analysis in the software is the best way to answer that question in terms of not just looking at what's the total efficiency for this pump, but what's my total energy consumption. The next question is a VSD a good means to measure energy consumption on a PCP? Absolutely. The VSDs, VFDs, they will record the current, and that current measurement should be very accurate. They know the voltage, the current, so you know the energy consumption. What it can't do is tell you the efficiency, because whatever, especially like I said, when we're talking about the surface equipment, when they have the torque measurement that's on there, that torque measurement is making some assumption of the efficiencies of the drive equipment. So if you're then using that to calculate, you're just going to calculate whatever the VSD was assuming for efficiency. But for total energy consumption, yes, it's measuring it directly. So yes, it should be a good way of recording that information. We use a PMM when the crew dismantles electrical cable. They should wait some time or dismantle directly after shutdown. This is a very important point. It's getting off the question of energy consumption, of course, but if you're using PMM systems, it's something to be very cautious of. The PMM generates power when it's run in reverse. So even though you've disconnected the power cables, if something happens to make that pump rotate, backspin, for example, it will generate power. And there have been serious incidents around the world because of that. So anyone working with a PMM needs to be aware of this. There are safety procedures that if they're followed, everything can be safe. So if it's a surface PMM, you can obviously see if it's rotating, and if there's any rotation state, away from the cables. When you're doing something in the well, like pulling the rotor out of the stator and that surface drive, we know that when we pull the rotor out of the stator, it may drain a little bit of fluid. You might see some rotation. So while they're doing that, nobody should be near the electrical terminals and things like that. If it's a downhole system, a downhole PMM ESPCP, you can't see it, so you don't know if there's something happening. If the well, even during installation or pulling, that fluid could be moving through the pump and causing it to rotate and generating power. So the ends of the cable may be energized, even though you're during installation or pullout. So there's procedures for that to basically short and ground the ends of the cable to make sure that's not causing a safety concern. So there are procedures there. But yeah, in general, if you're working with a PMM system, whether it's a surface drive or downhole drive, you need to be aware of that as a safety concern, and the people who are working with the cables need to check for voltage before they do anything that would put them at risk. I hope that answers the question there. I think I'll just review these questions and make sure I've tried to answer everything here. I think I've got everything. Oh, it says there's one more here. Okay, yeah, Alban had answered this one and said he's send an email because it was a different one. Yeah, so someone had asked about rod centralizers. I'd be happy to answer that offline. For the different, in terms of energy efficiency, for rod centralizers, the ones that spin through, have a shaft that rotates through a sleeve that stays stationary, those are the best for energy efficiency because you're reducing that contact diameter. You have instead of having the full diameter coupling rotating on the tubing wall, you have a smaller shaft that goes through the coupling that's rotating in against the stationary sleeve. So that reduces the torque. Okay, so we've come to the end of our time here, unless there are any new questions. Again, with the time delay, if you're typing it in right now, I might log off before I see that. So I would like to thank everybody for attending today. If you have questions beyond what we've answered here or go more detail on anything that was in the presentation, please feel free to send me an email. It was on the last slide that we showed there, or if you were emailed the link to this webinar, that would have come from my email address, so you can just send me an email there. Happy to answer any questions you have. As usual, the recording of the presentation will be put online probably in about 2 weeks. So the recording and the copy of the slides will be made available on our website, so you can come and see that or share it with your colleagues. But in the meantime, if you have any questions, please send me an email. But other than that, thank you very much for attending, and hope we'll see you again. Thank you.